idea. Thank you for reminding. And yeah, every once in a while, those recordings being deleted by system. So what I do is I found a way to recover those recordings. So I recover them. So if you don't see a recording, the link that I sent you, just let me know so I will recover it because it looks like they decided to automatically delete all the recordings we produce. I don't know who's come up with this idea. That's awesome idea, of course, but I found a way to recover. So that's great. But again, don't wait for months to watch those lectures because looks like college is very anxious to get rid of those recordings because there is not much memory space they purchased. And that's the main thing why the recordings don't stay there for a long time. And that's why advice is if we had, say, lectures during the week, well, watch those recordings over the weekend because they might be gone in next week or two because I'm not the only one who does this recovery. There's somebody else has access to recordings and they just delete them. And if they delete them permanently, then, well, they be unrecoverable. That's good to realize. But anyways, I just went this morning to the Zoom recordings and I recovered quite a few of them. So they should be still available. So that's to Zoom recordings. But if you're in class, then probably don't really need that. But it's still a good idea if something is unclear to maybe try to watch it, but not wait for too much time. So anyways, this exercise I selected because it looks like here they have division first and then multiplication second, and that's not actually the way to go. So the first thing I'm going to do is I'm going to square because the exponents come first, right? So I'm going to square 8 and 2. So what we're going to have is 64 here, right? Minus 16. And then the 16 will be divided by number 4. And then it'd be multiplied by 4, right? And then we subtract 3. So the question is, what you're going to do next? Are you going to multiply 4 and 4 or you divide 16 by 4? And the wrong answer will be to multiply because we do from left to right. Even though there is a multiplication and division in this little phrase, but actually there is a brother for PEMDAS, it's PEDMAS. In other words, that division or multiplication could be put in any order. Whatever is on the left, you do first. So since division is on the left, you do it first. So you're going to have 4 in here. So what I get then is 64 minus 4 times 4. And then when I subtract 3, I'm going to be subtracting from 64 a couple of numbers, such as a 16 and 3. And I'll get the answer. So 64 minus 16 will give us what? 48, something like that, right? See, I write down all of my calculations. So this way I don't miss any steps. And when I subtract 3 from 48, it'd be 45. On contrary, if you did multiplication first, you would get 16 divided by 16, you get 1. So when you subtract 64 and 1 and 3, you will get 60. But the answer is not that. I say, Alex, how do I know? How can I check it? Well, of course, you have a little friend called calculator, and that's other thing that I shouldn't underestimate because some people will just use a calculator, put it in a calculator, right? So if I just enter to double check 64 and I subtract 16 and I divide this by 4 and multiply by 4 again, right? And then subtract 3. Look at what I'm gonna, well, no. See, I wasn't careful. I was kind of hurrying. So let me clear this out because the calculator actually shows what I'm entering. So when I divide 64 by 4 and then I need to put times 4 here, right? and then -3, then the answer is indeed 45. So the point of story that yes, you can technically put this in a calculator. So this order of operations is good to know, but if you have a calculator, then you can double check. So that's the part that, again, I'm sure most people are familiar with. And if you're not, then do more problems here, but it's not going to take too much time, right? So you can make a print screen of this page with exercises. And when I go to the next page, it's already practice plus, so you don't have to worry about this at all. So I'm going to enter section 5.3. That's another section that should be familiar. It deals with fractions, and they show various fractions. And since fractions could be treated as ratios, then they have a name, rational numbers. And here are the examples of fractions that of rational numbers, such as 1/2 or -3/4, or numbers 5 and zeros. And one may wonder why those are ratios, because they're whole numbers. Well, because they can always be turned into 5/1. So you can also write these as fractions. So what's the point of writing number as fraction? Let me see, if it's 5. Well, to show that you have numerator and denominator both whole numbers. 5 and 1 are whole numbers. So that's the idea. So we divide two whole numbers, and that's how you produce rational number. Maybe they could be actually simplified and you get 5, but in the case of 1/2 or 3/4, they can't be really simplified because they're the fractions in lowest terms. But you can write them as a 0.5, right? As decimals, in other words, or -0.75. So those decimals that people say stop, don't continue forever, or people say terminate, terminal decimals, those are rational numbers. There is actually infinite decimals also, such as for presentation of 1/3, which is going to be 3, 3, 3, etc. Sometimes people write this as a 0.3 with a bar above. That means that 3 repeats infinitely many times. So that's infinite decimal, but people say infinite repeating decimals. So it repeats again and again and again and again. And that's another possibility for those fractional numbers. So maybe terminal decimal that stops, maybe infinite repeating decimals that just keep on repeating, and so forth. So I guess the fractions could be treated as decimals as well. So let us maybe go to the end of the section and do some of the exercises, because I'm sure that you already worked with fractions in previous math classes you took. And if you forgot, well, we'll refresh your memories right now. So fractions, and here's the exercises at the section end. So let me take a look at these little problems. So let me get this cleaned a little bit. Maybe I'll clean this writings real quick. So various fractions you can reduce to lowest terms, like exercise, for example, number 4, that talks about 16/64. Some people may notice that 16 times 4 is 64, and numerator is 16 times 1. So I can see the common factor of 16 and on the top and on the bottom. So I can cancel that 16. I want to say, what does that mean? Cancel. All of a sudden you cancel. Well, the reason I can reduce that 16 is because I multiply by 16 and then I divide by 16. So I made my fraction 16 times larger and then 16 times smaller. So I didn't really do anything with the fraction. And that's the reason why we don't have to keep that 16 there at all. We just get rid of it, because fraction is really 1/4. And you could see that this is 1/4 even from the beginning, right? Because if you divide 1 by 4, you get 0.25, the decimal way to write fraction, right? 0.25. And if you divide 16 by 64, let me do it with a calculator. You should also get the same exact result. So when I divide 16 by 64, I also get 1/4, do you see it? 0.25. So it turns out the result is the same. And that's the reason why you can cancel, because why would you need to keep those big numbers 16 and 64 on the top and the bottom? You can just put 1/4, and that's more compact and looks nicer. So that's why people like to cancel those fractions. Also, you could pull out the whole part from the fraction. For example, in exercise 24, people don't want to have fractions as 788 over 25, because it's better to see what would be the whole part, how many times 25 will fit into 788. So I start with 3 because 3 25s is 75, isn't it? So when I subtract there 3 and 8 comes down, so I have another 1. And when I subtract 25 from 38, what I'm left with is number 14. So I can say that this is going to be 31, the whole part. So my quotient here, the 31, I put as a whole part. And then how many 25ths are left? And turns out the remainder 25ths. Why did I put 24? I need to wake up. 25. So a remainder, which is 14, I'm still to divide by that denominator 25. So 25 is in denominator. And what remains, it's called remainder, is still to be divided by 25. I couldn't really make it, so I just stopped. Some people will say, Alex, if you could continue divide, produce decimals, you would get actually a point and some others. Yeah, that's another way, and that's what they do in the next exercises. But point of story that we produce so-called mixed number. Mixed means whole part and fractional part. So that's what they asked. You probably saw this mixed numbers before, but in that you could also divide 14 by 25 and get some decimals. Well, that's interesting. So how about if we try exercise like 39 that says, what if we try to, instead of that decimal, produce a quotient? Let's see, what do they want? Well, this is 4/10. So in other words, it's 4 over 10. See what they want? They want a fraction. So they just should have said fraction instead of saying quotient of integers. They just want to get a fraction. So it's really 4 over 10, 4/10. I say, Alex, I'm sure this could be 2/5 because it looks like I can divide n top and the bottom by 2. Yes, that's the way to give your answers. So 2/5, that's the simplest form, right? So you could also write your fractions in this lowest form. So that's another thing we looked at last time briefly, right? And all of these decimals you could also write as those fractions, like I think we did 48, right? So we have 10,000s and whatever else. So let us move to the next page and keep working with these little fractions. And looks like the problems are here until practice plus, so you can actually look at the exercises on that page. And well, you could just try to deal with some of those. Let's say if I start with exercise number, I think good one to start will be 72. That wants us to add 2 fractions with denominator 13. Well, denominator 13 will be also denominator for the end result. And if you add 5 13s with 2 of those 13s, then you just add 5 and 2 and you get 7 of those little 13s. So the point of story, if you have same exact denominators, then it's very nice because you just put those numerators together. You just add your numerators, and that's it. So what if denominators are not the same, like in a problem 81, for example? I say, well, then it's no good. Yes, then I need to make those denominators to be the same. So maybe I can start with something a little bit better, like 80, and then I'll do 81. So exercise 80 also has different denominators. So people will try to produce the same denominator. And turns out the largest denominator, 15, will work. So 2/15 already has that 15 in it, but the first fraction is 2/5. So how can I produce denominator of 15? And people say, just take that 5 and multiply it by 3, but you also have to multiply numerator by 3. This is not going to change your fraction. So the point of story, you can multiply any top and the bottom of that fraction by exactly the same number. That's allowed. So I multiplied by 3 because technically I could cancel those 3's. So the bottom will be 15 and the top will be a number 6, right? So that's what I have produced so far. And you probably already added those and produced 8 on the top and still 15 on the bottom. So that's what we did in arithmetic classes. We produced those common denominators. So we could add those little fractions or subtract. That was same idea. So if I try to add these two fractions in exercise 81, looks like 30, the largest denominator, I cannot produce out of 24. And turns out I need to start thinking how I can find the common denominator. And turns out that factor of 5 is here because 30 is 6 times 5. So what people say, just multiply 24 by 5 and you will get it. That'd be 120. So it turns out if I turn this into two fractions with denominators 120, then I'll be able to have this common denominator thing working. The reason is I can multiply 30 to get 120 by 4. 3 times 4 is 12, so I put 4 on the top and here as well. And I can also multiply by 5 my first fractional and top and the bottom. Did you ever see that before? Of course, this denominator is kind of crazy, it's too much. But as long as you found the same denominators, then you can add fractions. So now I just multiply numerator part, 5 times 5 is 25, right? And also 7 times 4 is 28. And this enables me to actually add those fractions. So denominator is 120. So when I add fractions, I just add numerators. And the result will be 53 on the top. 53 over 120. Yes, that was a little bit tedious. But I think on this page, well, my goal is just to have you maybe refresh a little bit of your arithmetic skills, just to make sure that you can see what's going on. Because every once in a while you need to add fractions or subtract or multiply. But I'm gonna say, Alex, I have a calculator for that. I know, but again, I can do a couple of problems here in this section just for fun. So how about if we try something else, which is not a standard, and looks like the next group of exercises here down below before practice plus is a little bit different. Because I'm sure if you took arithmetic classes before, then you can definitely do these exercises, no problem. So you don't have to waste your time. If you already know how to do these problems, you can do a couple of problems from this group and that should be good enough. Well, problem 105 is a little bit different. So it asks to find the ratio or rational number halfway in between of these two. So what do they talk about? How can I find the number in between of two? Let's say if you have numbers 2 and 4. What's going to be right in between? I say, Alex, in between is going to be 3. Yes, we can guess it, but technically to find it, I just find so-called midpoint. So I add those two numbers and divide their sum by 2. So when you take 6, right, 2 plus 4 is 6, and divide it by 2, you get 3. And that's the standard way to find the number in the middle, or so-called midpoint. And that's what they want in exercise 105. So they want to add these two fractions, 105. So it says 1/4 added with 1/5, oh, 1/3, sorry, 1/3, and divide the sum by 2. I say, you can do this with fractions also. Yeah, it's standard. No matter what you have for the numbers, 2, 4, or these two little fractions, you still add them up and divide the sum by 2. I say, well, Alex, how can I do that? That bothers me. Well, what bothers me here also is those denominators, right? That's the part that is not very nice. And it turns out there is a way to clear those denominators, to get rid of them, so they no longer bother us. And the way to do this is to multiply and denominator and numerator of this fraction by the same exact number. And that number will be 4 times 3, 12. So what you do is you use so-called common denominator, just like we did for the previous exercises. And you multiply and divide by 12, so these 12s can be canceled, nothing will change, but you actually distribute this 12. So what you do is you times by 12 here, and you times by 12 here. So you actually multiply by 12 each entry of your fraction. See, why would you do that? Well, because look at what's going to happen. 12 and 4 will cancel, give you 3. 12 and 3 will cancel, give you 4. So when I continue with this, I'm going to get numerator, which is 3 plus 4. No more fractions. That's the point. See, really? Well, look at what we get. 12 over 4 is 3. So times 1, we multiply, and it's just a 3, right? Plus sign. And same on the other piece. 12 over 3 is 4. Times 1 is still 4. And denominator will be 12 times 2, which is 24. So for the answer, we have 7 over 24. That's the fraction right in between. Can you believe that? If you take a fraction 1/4 and 1/3, then in between of them, right here in the middle, will be that 7/24. How about that? So that's just unbelievable. Yeah, kind of. But it's standard procedure. So you just add those two on the sides and divide by 2 and get the answer. So you find so-called average. So you can practice, maybe do another one like 107 for fun, and that'd be good enough. I don't want to be stuck with this section for too long because, again, it's familiar stuff, I hope. And I want to move to the next section that is a little less familiar. Section number 5.4 that talks about so-called irrational numbers. So what does that mean? Irrational numbers. Well, it turns out those are also decimals, but they're infinite decimals. So if you, for example, consider a square root from 2, this number actually continues infinitely. I'm going to say, Alex, we already had such a decimal, 1/3. You told us it's infinite decimal also, right? 3, 3. Well, with 1/3, 3 repeats. 3, 3, 3. But with a square root 2, we don't have anything that repeats in here. Just keep on getting the different digits. See the difference? When you have square root, it's not repeating. And people say you cannot write it as a fraction. And that's the idea. So square root 2 is not a fraction. See, how come it's not a fraction? Well, it's a square root. Turns out you cannot write it as a fraction. They actually proved this in number theory class, but here we don't have to do the proofs. Turns out we just should believe that square root 2 is not a fraction, square root 3. So any square root that you cannot nicely extract, like for example, square root 4, you can extract, it's 2, right? But square root 3, square root 5, square root 6. So lots of square roots are going to be not fractions, and we call them with a special name, irrational number. Not ratio, but not ratio means irrational. So they're not ratios, they're not fractions. And that's what this section is talking about. Talks about irrational numbers, and that's what they're actually coming up with, various square roots that you cannot nicely extract, like square root 5 or some others. Irrational numbers like square root 17, for example. So they say that's disappointing. Well, it's not, it's okay. So we just have various square root stories here. And I think that's what they're actually working with in this little section, with those square roots. So I'm sure if you took algebra class, you already worked with those square roots. So I can take a little look at exercises in 5.4. So let me just clean all the stuff I produced so far. Stop share the screen. Like that. And well, just look at these square roots. I say, Alex, I like number 1, square root of 9. This is 3. Do you know why this is 3? Because 3 squared is 9. So it turns out you always check the square root extractions by doing the squares. Square root, square, their opposite operations. So I can extract, let's say, square root 121, that's going to be 11, because 11 squared is 121. And square root 144 will be 12. Say, Alex, how would you know that? Well, I've been preparing all night, so I've memorized them. So it turns out you can just check this with calculator. So if you try square root 44, 144, for example, so square root here, 144, and it is 12. So you don't have to memorize, you can just use a calculator for this. So, well, people every once in a while encounter such number as 121, so it's good to know it's 11 squared, or 169, which is 13 squared, or 225, which is 15 squared. Square root will be 15. But you don't have to worry about this. You can just put this in a calculator. In fact, that's what the next group of exercises says. Put this in a calculator. Let's say exercise 15, for example. What if you have a square root of pi? You say, what is pi? Well, pi is another irrational number. Turns out it's 3.14, and then it's more digits. Square root. I can extract from any number, so why don't I extract it from pi? So let me get a calculator, put a square root, and notice that pi is right here. You see what it is? You see, well, it's some kind of decimal. Yeah, so you could just copy this decimal, just decimal, square root of pi. Anyways, the message is you could just use calculator, and that's what actually they say here, but not for next group of problems. So let me do problem number 17 that talks about square root extracted from 20. And turns out in exercise 17 with a square root of 20, I could treat that 20 as 4 times 5. Factor it. The reason I factor it with a 4 and 5 is because I can square root number 4, right? I can square root number 4, it's 2. We just did it. So the answer we can write with a square root. So it's going to be 2 multiplied by a square root from 5. Just like that. So you can use this idea of perfect squares. 4 turns out is a perfect square. It's 2 squared. So you square root just a part of the number and leave square root untouched. See, that's kind of odd. So why would we do that? I don't know, just for practice, I guess. So if you do another one, let's say exercise 24, 3 is going to be multiplied. So just leave it for now, 52. What I want to do is factor 52. See if there is any perfect square present. So I have 26 times 2, and then I factor 26 with 2 and 13. I can see how to write this, 52. I can write 52 with a factor 4, right? And factor 13. You see, instead of 52, I write 4 times 13. So what we can do now is keep that 3 the way it is and times this by square root 4, just like I did in the previous exercise, and by square root 13. And then square root 4 is 2, right? So I can extract that piece. And that's the reason why I do this whole thing. So we're going to have 3 times 2, which is 6. And there is still square root 13 is attached to it. That's the answer. Notice that 13 I cannot square root, so I leave it alone. So the whole point of this next group of exercises is to be able to produce one single square root out of 2. Like say problem number 43, when you add 1 square root with another square root of 5, well, you're going to get 2 of them square roots of 5. Because you add 1 and 1, you get 2. And say, okay, Alex, how would you add number 47? Well, let me work on square root of 20. That's the one that I think I can simplify. And I should, because 20 is 4 times 5, right? So we get a radical 4 times radical 5. And instead of radical 4, I have 2 square roots of 5. And please notice that's just what I need in this exercise, because I have already square root of 5 that I add with 2 square roots of 5 that I replace my number 20 with. So how many square roots of 5 do I get? 3 of them, 1 and 2 more will be 3. So people sometimes call these like radicals, like square roots. Both are square roots of 5. Let me do one more here, like that. 52 exercise. So these things we usually do in intermediate algebra class, and I hope you already saw these things before. And if not, it's fine. You can look at them now and maybe redo the same problems I do today over weekend. So I noticed that these numbers such as 75 and 12 could be both factored with 3 and a perfect square. So what I have here is a 4, and then I have a square root 4 times square root 3, right? That's my first piece. Plus, second piece, I still have a 2, but then I also put square root 25 and another square root of 3. So that's how I start. Reason I do this is because I want to simplify those radicals. So this is going to be 2, and this is going to be 5. So what I get now is 4 times 2, 8 radicals 3. Do you see that? 8 radical 3. Added with 2 times 5, which is 10 of this radical 3. So what's the answer? How many radicals 3? 18, right? 18 times square root of 3, 18 radicals 3. So like radicals, that's all we care about. That's interesting, right? So let's see what else is in this section. Maybe I'll scroll down a little bit. Well, it's pretty much over in here. So what about next page? Well, on the next page, there is a little group of exercises that says rationalize denominator. I don't think we're going to use it much, so I can let you skip this. So this denominators don't need to have square roots. So technically what you do is multiply by square root 7 in the top and the bottom. But I don't know what this is for. I don't think we're going to use it in our class. So it'll be 7 on the bottom, 21 times square root 7 on the top. And then you can actually simplify a little bit, right? You can divide 21 by 7 and you get 3. So the answer is going to look like 3 square root 7. But again, it's just manipulation with some algebraic pieces. So I don't think we need that. So for homework, you could just do problems on the previous page here, and that should be good enough. And of course, if you have more questions for me, so let me clean this so you can make a print screen of this page so you can do this for homework. So if you have questions next time, we'll definitely look at them. So I'd like to take a sneak peek into the next section just to see what's in it. So next section is 5.5 that continues the story of numbers, and they actually talk about some numbers such as rationals and irrationals. So we just talked about those as well. Notice that square root 9 I can extract, it's 3, right? But square root 10 I can't. So it turns out that I can say that my rational numbers, fractions, oh, it's right here, part D, rational numbers, are going to be all of these except for square root 10 and pi over 2, turns out. So they be minus 9, minus 1.3, 0, 0.3 with a bar, because we already know it's 1/3, right? We just looked at that number. It's a ratio. We can write it as fraction. And square root 9, because it's just a 3. Remember, all of these you can write as fractions with denominators 1, and negative 1.3 is actually 1 3/10, which is also a fraction. You could actually say it's negative 13/10, right? So it's a fraction. You can divide a couple of whole numbers and get the fraction, but not with square root of 10, and turns out not with pi. So number pi is irrational number. So irrational numbers will be pi over 2 and square root of 10. So it turns out the numbers split into 2 categories: rational, which is fractional, and not fractional, irrational. So irrationals are ones that deal with pi, that's a special number, and various radicals. And whatever else, we get like those rational numbers. And turns out that all of these numbers will be called reals, because you can put them all on so-called real number lines. So you can write these numbers, you can find their positions, such as if 0 is here, the number pi will be somewhere 1, 2, 3, so close to this. So pi is going to be here. The square root of 10 is going to be someplace also around this area, square root 10. So the point of story that all numbers that you can put on number line called real numbers. So everything that we're given here in this group of numbers, people actually say set of numbers, will be called real numbers. Yes, you can again put them on number line. I say, okay, Alex, what are the first three pieces of story? Well, first three pieces require a little bit of explanation. So natural numbers or naturals, we already saw in this class. We even gave them a special name like n with that thicker part in the middle. So they start with 1 and then go 2, 3. So the numbers that you use to count things. So 1, 2, 3, 4, 5. So those are most popular numbers they call naturals. And the only natural number I see here is a square root 9 because it's actually 3. They just write it such a way to maybe hide it from us, but they cannot really hide from us anything, right? So natural numbers. There is another set of numbers called whole numbers. Whole numbers, and that's the part B, that's the next question. And turns out whole number set is exact same 1, 2, 3, and so forth, but with only one extra number, number 0. So they add 0. So it turns out if you look at the whole number set, then 0 will be in it because I can see 0 here, right? And I also see that square root 9, which is 3, is still present. So whole numbers, when you say, what kind of set is that? It's the same thing, but 0 in it? Yes, so that's whole numbers. And then they also talk about so-called integer numbers, integer numbers or integers. And they give them a special name. They put that Z with a big, thick part here, just like with n, thicker part. And those be, again, the same numbers, 0, 1, 2, 3, ... but also opposites, like -1, -2, -3. So we get also negative numbers in them. So such as number -9 will be present. So in integers, we have -9 and also 0 and also square root 9. So it looks like these sets, they just get bigger and bigger. So naturals have 1, 2, 3, then we get extra stuff, 0, they get whole numbers. We get extra stuff, negatives, we get integers. And turns out all of these are also going to be rational numbers, but rationals add a little bit more. They add those decimals or fractions to those. That's interesting to think about, right? So what numbers we're dealing with in these classes. So you keep dealing with those radicals and other numbers, other real numbers all the time. So there are numbers and we have various little examples here. So let me try exercise. I don't want to overload you today. I know it's Friday, so maybe I'll just do problems on the first page here. First group of exercises, first 4. So let me try number 4 exercise. Just find, so for exercise number 4, find, let's say, part C, integers. So what will be integer numbers? Well, it's good to know what this means to find integers. Those are like whole numbers and plus minus signs with them. So in exercise 4, I can see number -5, right? I can see number 0. And I have number square root 4, which is actually 2, right? And those are my integers. And that's it. Okay. How about whole numbers? Part B. Whole numbers. Well, for whole numbers, I got 0 and 2, right? Square root 4, which is 2. So please notice that for whole numbers, there are no negatives. No negatives. Okay, so maybe exercise for you for a little quiz. How do you feel? I'll also ask you to find some integers. I'm sure that's going to be nice question. So what about exercise number 2 for quiz, but only find integers. Find integers. So just list them, what you see as integer numbers, and here again they are integers, among problems, among numbers that you see here in exercise number 2. So I'm going to stop recording at this stage.